This lecture is going to discuss gravitation. So, as we've learned before, Newton's insight was that gravity didn't just work on Earth, it also was the force that kept the moon in orbit around the Earth. And he realized that that force of gravity was proportional to both the mass of the moon and the Earth, or the mass of the Earth and the sun, or even the mass of any two objects that are next to each other, like you and the table or you and the seat. That gravitational force of attraction was between any two masses. It's proportional to the masses, but it's also inversely related to the square of distance. So that means that if you double the distance between you and somebody that you're sitting next to, instead of the force of attraction between you being half as much, it's 1/2 squared as much, or 1/4 as much. And if you triple the distance between you and your friend, then the force of attraction between you is not 1/3 as much, but 1/9 as much. Now, on the other end of it, if you were to decrease the distance so that the distance was 1/2 of the original distance, then the inverse of a half is 2, and 2 squared would be 4, so the force would be 4 times as much. It's an inverse square relationship. Also, there is a constant that is necessary to keep everything working, and that's the universal gravitational constant. This value is 6.67 times 10 to the negative 11 newtons meter squared all over kilogram squared. The symbol for it is a big G, and it's not to be confused with the little g that we use for the acceleration of gravity, 9.8 meters per second squared. So the big thing about the force, the gravitational force, is that it is when you find that force, you're finding the force on both objects. Say if mass 2 was twice the mass of 1, the force of attraction between each one would be the same. Okay, there wouldn't be more force on 1 or on 2 because they have different masses. Because in that equation, right, it's proportional to both masses. So if I double one mass, I double the force on both bodies. So when we talk about the distance between the two objects, we're always talking about the distance between their center of masses. Remember that G is a very small number, and that means that force of gravity is very, very, very small. That's why when we talked about you and your friend feeling a force of gravitational attraction, you don't really experience that, do you? Because if you actually plug in, real numbers for your masses, and for, let's say you're sitting a meter apart, and then you plug in that constant, the force of attraction is super small. It's like something times 10 to the negative 6 or negative 8. Super, super small. So you're not going to feel that force at all. However, it's so important in nature because it is a very significant force when you're dealing with large, large masses like the Earth and the Sun and the Moon. It is the reason why objects stay rotating. It provides a centripetal force to keep the moon going around the sun, around the Earth, and the Earth going around the sun. Also, every mass will exert force on other masses. So if you have more than two masses, then the net gravitational force would be the sum of the gravitational forces due to each mass on that mass. Gravitational force between a point mass and a sphere. The force is the same as if all the mass of the sphere were concentrated in its center. So just because the object has some dimension to it doesn't mean that that we look at what's happening to each part of this. We once again use the point particle system. We condensed all this mass down to a point particle, and we think about, for instance, this potted plant is attracted to the Earth. So the Earth would be pulling down on the center of mass equal to its weight. And remember that the pod is pulling up on the Earth with the same amount of weight or force. So what is the force of attraction between two 40-kilogram objects located 1 millimeter apart? When we plug into our formula, we'll plug in our equation, G, 6.67 e to the negative 11, times 40, divided by 0.001 squared. Note that I had to change millimeters to meters. And the force of attraction that each mass experiences is 0.107 newtons. Now, if I double this mass, like if I double one of the masses, then this would be twice as much. If I double both of the masses, it doubles twice. It's 4 times as much. If I double this distance, and keep the masses the same, the force will be 1/4 as much, etc. So what about the gravitational force on objects at the surface of the Earth? The center of the Earth is 1 Earth radius away. So this is the distance we use. We use the radius. So for example, if I were to plug in my mass and the mass of the Earth and the radius of the Earth squared, I would end up with my weight in newtons. Now, we've learned that we can find weight using mass times gravity, right? Because that weight causes us to accelerate. It is the force that causes us to accelerate at 9.8 meters per second squared. So if you plug in our weight into F equals ma, A is g, and that's where we get the mg from. We can also find our weight using the universal gravitation formula, as we've discussed right here. We can set those equal to each other, right? Remember, little m is my mass. And I could also find it using m times g. So that means that if we cross out these m's, that we can find a formula for g for any planet. And for Earth, g would be the mass of the big G, times the mass of the Earth divided by the radius of the Earth squared. For Jupiter, it would be the mass of Jupiter instead, and the radius of Jupiter squared. So you can find g for any planet. And remember, we said that g on Earth is independent of mass. If the only force acting on the object is its weight or gravitational force, then if there were no air at all on Earth, a hammer and a feather would land at the exact same time, just like they do at the moon, because the acceleration of gravity, g little g, is independent of the mass of the object. Notice that this holds that up, right? That this verifies that. The mass of the object will go out of the equation. Now, that means that since gravity does have some dependence on how far away you are from the center of the Earth, if we use the value of 9.8, right? But if you go up to the Mount Everest, 9.8 changes significantly. Okay, and the reason it changes is because Mount Everest has a significant, a relatively significant different distance from, it's a little bit higher, thus more distance added to the distance between you and the center of the Earth. So remember, if you increase r, the inverse square will happen. So your weight will go down. And of course, if you go up and to where the space shuttle or the International Space Station is, which is very far above the radius of the Earth, right? Then what happens is your weight decreases to a very, very small value because the acceleration of gravity changes. So the acceleration of gravity is also called the gravitational field strength. It's how strong the gravity is at that point or location. So gravity and the force of gravity, weight on Earth, change with the square of distance, inverse square of distance. Oops, that's not what I wanted to do. So as you get up higher, eventually the acceleration of gravity is going to approach zero, and you would be considered, the object would be considered weightless. Also, what Newton found was that he could predict the mass of the Earth with his equation. So he knew what gravity was on the Earth, and he just rearranged the equation for gravity. And he found that he could predict, and he predicted the mass of the Earth within a very close accuracy, just by taking the estimated radius of the Earth, gravitational constant, and 9.8 meters per second squared that Galileo had determined, and he could estimate the mass of the Earth, and he did a really good job. So that means that we can too. Like if we go to the moon and we measure gravity there, we know how big it is, we can estimate the mass of it as well. All right, the rest of the PowerPoint in chapter 12 is about Kepler's laws. I am not going to go over these in detail, but you may be interested in his laws of planetary motion and the significance that they had, and I feel free to read them and look over the PowerPoints, but I'm only going to concentrate on gravitation in this unit.